In this video, we're going to continue working with Green's theorem and look at a few more examples that involve using it. So to get started, let's look at the following example. So let's say we want to evaluate the line integral over curve C of 3y minus e to the sine x dx plus 7x plus the square root of y to the fourth plus 1 dy. All right, and I know this is a little hard to read here. That exponent in the second term there is y to the fourth, not y to the ninth. All right, so we have this function there, and we need to talk about the curve. So C is the positively oriented circle. X squared plus y squared equals 9. So the circle centered at the origin of radius 3. Now before we use Green's theorem to evaluate this, let's take a moment to think about how we would approach this if we did not know Green's theorem, if we just had to compute this like a normal line integral. Right? So our first step would be to parameterize our circle, and that's not terribly difficult to do. In this case, it's a unit circle of radius 3, so one easy way to do that would be to take the parameterization 3 cosine t, 3 sine t, and let t range from 0 to 2 pi. Right, so that would be a parameterization for our curve C. And then we would have to substitute these values into our integral. If we had to do this, we would have the integral from 0 to 2 pi of 3y minus e to the sine x. So it's going to be 3 times 3 sine of t, so I'll go ahead and make that 9 sine of t. E raised to the sine of x, so e raised to the sine of 3 cosine of t. Then multiplied by dx, which is negative 3 sine t, plus, and then we have this other term over here, which I think you can see is not going to be extremely pretty either. We're going to have the square root of 3 sine t to the fourth plus 1 in there. And so this is just going to be, how you have to find an antiderivative of e to the sine of 3 cosine t multiplied by some various things. That's just, even if we could do that, it's going to be very, very difficult. So the example we saw at the end of the previous video, we could do as a line integral and compute 3 line integrals over the sides of that triangle. This one, the integration just isn't there. It's not going to work. And so we need to come up with something else that'll work. And that's where Green's theorem comes into play. All right, so let's get rid of this nonsense. And let's apply Green's theorem. All right, so we do have a simple closed positively oriented curve. And so the partial derivatives of p and q are going to be continuous on that curve, or on that region inside the unit circle. So that's good. Right? And so we have our function p is 3y minus e to the sine x. We have function q, the scalar field q, which is 7x plus the square root of y to the fourth plus 1. And that's a 4 again. Right? And so our integral that we want to compute is equal to the double integral over region D. And just to be clear here, the region D, okay, we have the positively oriented circle. The region D is the region inside that circle of radius 3 of del q del x. All right, when we differentiate q with respect to x, we get 7 minus del p del y. The derivative of p with respect to y is 3. dA. All right, so we saw when we tried to do the line integral as a line integral, we saw we had this monstrous function that we had to find the antiderivative of. Here we're going to we're going to integrate the function 4, a constant function. Now, the next step is to write this as a set of iterated integrals so that we could integrate over this region D. However, this region D is the interior of a circle, and so the region is best described using polar coordinates. And so we want the area inside that whole unit circle. And so the easiest way to represent that region is by looking at R ranging from 0 to 3. So that's everything from the origin out to the circle of radius 3. And we want theta to go all the way around. We want the entire circle, right, which would be 0 to 2 pi. Right? If we wanted just the top half of the circle, we would want 0 to pi. If we want just the first quarter of the circle, we would go 0 to pi over 2, and so on. But in this case, we want the entire circle, so theta should range from 0 to 2 pi. Right? And so converting this integral to an iterated integral with polar coordinates, we're going to have the integral of 0 to 2 pi, which is d theta. We're going to have the integral from 0 to 3, which is dr. Of this function 4, and remember that when we convert to polar coordinates, we do have to multiply by r. So we're actually integrating the function 4r over this region. Right? So once we make this conversion, this becomes a relatively simple integral. This is the integral from 0 to 2 pi of the function 2r squared evaluated from 0 to 3 d theta. So integral 0 to 2 pi, we have 2 times 9, which is 18, minus 0, so 18 d theta. And so this is just 18 times 2 pi, which is 36 pi. Okay. And so we saw that as a line integral, this is virtually impossible to compute. But in this case, being able to apply Green's theorem, because we have a simple closed positively oriented unit or circle here, we're able to use Green's theorem, write it as this double integral of a relatively simple function, the constant function 4, and then just a quick conversion to polar coordinates makes this a relatively simple integral to do. And so let's look at a different example of Green's theorem. So both of the examples that we've done so far, we've looked at computing a line integral by rewriting it as a double integral. And here we're going to do the reverse. So here, let's say we're given a vector field, f of x, y, and it's going to equal the square root of x squared plus y squared minus 2 times I plus the square root of x squared plus y squared minus 2 times j. Right, so in this case, both of the component functions, p and q, are exactly the same. And we're going to let c be the circle x squared plus y squared equals 4. So we have our vector field, f, we have our curve c, and I'm assuming that c is oriented positively, and it's of course a closed simple curve by the nature of a circle. And what we want to do here is we want to evaluate the double integral over d, the interior of the circle, of the function del q del x minus del p del y, right, all dA. So you could think about how you would compute this double integral just as a double integral using Fubini's theorem and iterated integrals. We would want to compute the appropriate derivatives here, del q del x and del p del y. And those are both computable with what we have given, but notice that we are going to get some complicated derivatives. We have a chain rule in each case with the square root of x squared plus y squared, and then we have to take the derivative of the square root, multiply it by either 2x or 2y in each case, and then we'd have to integrate that function over this circular region, which we would have to convert to polar coordinates to do. And while it's possible to do that, it's going to be much easier to rely on Green's theorem, which will tell us that this particular integral is just the line integral of this particular vector field over the circle. And what we can observe from this particular vector field is if I pick a point on my circle. So let's pick a point AB. Right, and let's assume this is a point on curve C. Right? Well, then if I take P of AB, remember P is this first function, the first scalar field in my vector function. So we're going to take square root of a squared plus b squared minus 2. This is P of AB. Doesn't look like this helps us at all, but remember AB is a point on circle C, which tells me that a squared plus b squared is equal to 4. So we know this is just the square root of 4 minus 2, which is equal to 0. And similarly, Q of AB is actually the exact same function. Q and P are the same function, so Q of AB is also going to be 0 by the exact same work as showing that P of AB is equal to 0. So for every single point on this circle C, the functions P and Q are identically equal to 0. Right? They're obviously non-zero at points off of the circle, but for the line integral, we don't care about those points. For the line integral, we just care about the points on the circle C. Right? And so Green's theorem in this particular case tells us that the integral that we want, the integral over D of del Q del Y, or del Q del X minus del P del Y, this is equal to the line integral over the circle x squared plus y squared equals 4, which we called C, of the function P dx plus Q dy. Right? And as we just saw, on this circle C, the P function is just 0, and so is Q. Right? And so if we integrate the 0 function over any curve C, we get something equal to 0. So this integral, this double integral, has to be equal to 0. We don't have to go through the process of finding those derivatives, subtracting them, converting everything to polar coordinates, and then actually integrating. We see that when we do all of that, we're going to get 0 as our final value. All right, so let's look at one more example here. So let's say we wanted to evaluate the integral over curve C, which I'll describe in a second, of y squared dx plus 3xy dy, where curve C is going to be the boundary of the semi-annular region, and I will draw a picture of this. So it's the boundary of the semi-annular region D in the upper half plane between the circles x squared plus y squared equals 4, and x squared plus y squared equals 1. All right. Again, we have our functions p and q, which are y squared and 3xy. These are going to have continuous derivatives of all partial orders. So we can use Green's theorem, assuming our curve is thought of in the correct way. And so the way that we want to think of this curve, we want the area between these two circles in the upper half plane. And so this will be -1, -2, 1, and 2. I guess we'll have 1 here and 2 there. So we have the unit circle, x squared plus y squared equals 1. In the upper half plane is that region, is that curve there. X squared plus y squared equals 4 is the upper half plane is that circle there. And so our curve C is going to go around this region between these lines. So if I start at the point 1, 0, the curve is going to go over to 1, 2. It's going to traverse the circle there, go over to -1, and then along this other curve, other circle, 2.1. And so our region, or our curve rather, looks like this. And notice it has to be positively oriented to apply Green's theorem. And so it has to go counterclockwise. Right? Now, in order to compute this line integral, again, y squared, 3xy, dx, dy are not going to be hard to compute, typically. But notice that we would have to compute the line integral on 4 different curves. We have the bigger circle, x squared plus y squared equals 4, the top half of that circle. We'd have this little segment on the negative x-axis. We have the top half of the unit circle, and then we have this little segment on the positive x-axis. So we'd have to compute 4 different line integrals on 4 different curves. And again, not difficult, but it would be tedious and it would take a little bit of time. However, we have this region between the circles, which we call D, that semi-annular region. And Green's theorem says we can write this line integral as a double integral over that, and we can quite easily describe that region using polar coordinates. So that's exactly what we're going to do. So Green's theorem says the following. It says the integral, our original integral, the integral over c of y squared dx plus 3xy dy is equal to the double integral over that semi-annular region D of the derivative of q with respect to x, which would be 3y, minus the derivative of p with respect to y, which would be 2y. And of course, this is just the double integral of the function y. Now, in order to set up an iterated integral using Fubini's theorem, we need to find bounds for our region, our semi-annular region. And since this region is built out of circles, it makes sense to use polar coordinates for this particular reason, or for this particular region. So if we look at our region D and try to describe it in terms of polar coordinates, we see that the region lies between the circle centered at the origin of radius 1 and the circle centered at the origin of radius 2. So between x squared plus y squared equals 1 and x squared plus r squared equals 4. And so that means r in polar coordinates has to lie between 1 and 2. On the other hand, we only want the top half of this region. And so we only want theta to range from 0 to pi. We don't want to go to 2 pi. We don't want the entire semi-annular region. We just want the top half. And so we get these particular bounds on our polar integral. Right, so when we go to convert this, we're going to have the integral from 0 to pi of d theta, and then the integral 1 to 2 dr. Right? We have our function y in polar coordinates. Y is r sine theta. And remember that when converting to polar coordinates, we always must multiply by r. So we actually have r squared sine theta. Okay. So when we go to convert, or we go to compute this, we first integrate with respect to r. So I have 0 to pi. And again, that's r squared sine theta. So that will be r cubed over 3 sine theta. Thinking of sine theta as constant in terms of r. We're integrating from 1 to 2. So we have the integral from 0 to pi of the function 8/3 sine theta minus 1/3 sine theta, which of course will just be the integral of 7/3 sine theta. So anti-differentiate that, we get negative 7/3 cosine theta. Needs to go from 0 to pi. And so we have negative 7/3 cosine of pi is -1 minus negative 7/3 cosine of 0 is 1. And so this is just 7/3 plus 7/3, which is 14/3. So the value of this particular line integral is 14/3.